Section 2.9, Heteronuclear Molecular Orbitals. This is the MO diagram of two different atoms, A and B. This is one atomic orbital of A. This is a atomic orbital of B. They have different energies, and they can form two MOs. This is bonding MO. This is anti-bonding MO. The shape of the bonding MO is similar to the lower energy AO. The shape of the anti-bonding MO looks like the shape of the higher energy AO. And again, let's look at the energy. The energy of the bonding MO is even lower than the lower energy AO. The energy of the anti-bonding MO is even higher than the higher energy AO. So again, the analogy is this. A has $20, B has $100 after interaction, some business transaction. B now has even more money, $110. A has less money, only $10. So that's the essence of the energy change from AO to MO. Now let's look at the interaction between A and B from the perspective of symmetry. A and B must have the symmetry along the direction of the bond. All right. So, for example, if A has a nodal plan, let's say a p orbital has a nodal plan that contains the bond axis, and B is a s orbital without a nodal plan. All right. And then A and B cannot interact with each other. However, if A still is the p orbital, but the nodal plan does not contain the AB axis. Let's say this p orbital has a nodal plan perpendicular to the AB axis. All right, and then it's possible for this p orbital and this s orbital to have head-to-head interaction to form a sigma bond. All right, so you can't just look at the symmetry of the atomic orbitals individually. You have to examine their symmetry along the molecular axis. One more thing, if the atomic orbitals chi A and chi B differ significantly in their atomic orbital energy, then the interaction between these two will be small. Right? So if A and B differ significantly in energy, this MO is just mostly chi A. This is just mostly chi B, just not much change. The energy of this is going to be fairly close to chi A. The energy of this is going to be fairly close to chi B. So when do we have significant interactions? Well, first, A and B have the same symmetry along the molecular axis. And two, this chi A and chi B have similar energy. And then we expect to see strong interaction. Now let's look at this hydrogen fluoride. Again, you need to have the two interacting atomic orbitals with similar energies. So I'd say this 1s orbital, in theory, can interact with this 2s orbital, but the energy difference is significant. So this 1s is rather to interact with the 2pz orbital from fluorine. All right, so let's look at this 2pz orbital here, and this 1s orbital here. They can form a sigma bonding orbital and a sigma star anti-bonding orbital. We have one electron here. Together, they occupy the lower energy orbital. How about 2px and 2py? Due to the mismatch of the symmetry, these two cannot interact with the 1s orbital at all. Right? Still, it's hydrogen fluoride. Just a different molecular orbital diagram. Again, this is the 1s orbital. This is the 2s orbital of fluorine. This is the 2p orbital of fluorine. If you look at the scale of energy, I think this one is a bit more realistic. This one, almost, this 1s and 2p have similar energy, but that's not the case. Because this, in the hydrogen atom, I think the effective nuclear charge is the nuclear charge. It's +1. But in the fluorine atom, the effective nuclear charge, I think, is roughly 5. Although this fluorine has one additional shell, there's a larger distance between the electron and the nucleus. Overall, I believe the ionization energy of the valence electron in fluorine is much more negative than this hydrogen. Therefore, I think this energy diagram is more realistic, with this 2p orbitals, much lower than this 1s. Alright, now let's look at this interaction. Again, the 2pz may interact with this 1s to form this sigma orbital. And also, this 1s can also interact with the 2s. So it's showing here. Although the energy gap is even greater, so from here to here, you have a larger energy gap than from here to here, but still, there's a little bit of interaction because they have the right symmetry. Alright? And then over here, you have just the 2px, 2py orbitals. And again, when you have 1s interact with 2pz here, you form two MOs, sigma and sigma star, bonding and anti-bonding. And then I would say ignore the red lines. Again, the red lines are making the picture more complicated. Just think of this 2 sigma interact with this 2s, or this 1 sigma is essentially the 2s orbital of fluorine. So just think of the interaction between these two. That will bump this 2 sigma a little bit up, this 1 sigma a little bit down. Alright, so this way you can determine the shifts of the MOs without drawing or looking at those red lines. Alright, but by the way, this horizontal line tells you these 2 pi orbitals are the same as the 2 atomic orbitals, exactly the same. Alright, it's just the naming here. When we are looking at the MO diagram, the p orbitals are called pi orbitals. Oh, this is much more complicated. This is carbon and oxygen forming carbon monoxide. Alright, and you can see 1, 2, 3, 4, 5, 6, 7, 8, maybe 20 red lines, so it's just a little too much for me, but we can imagine this carbon 2s, this oxygen 2s, they can form sigma bonding and sigma anti-bonding. Alright? And also, this carbon 2s may interact with the 2pz of oxygen. It's head-to-head interaction. This 2s can interact with this 2pz, head-to-head interaction. Alright, and then, how about the pxpy? The pxpy from here, pxpy from here, they form the pi orbitals. 2 pi bonding orbitals, 2 pi anti-bonding orbitals. Alright, so we have 4 electrons occupying the pi bonding orbitals. Alright, again, we have this 2s, 2pz, 2s, 2pz. So a total of 4 atomic orbitals forming 1 sigma, 2 sigma, 3 sigma, and 4 sigmas. So over here you can see 1 sigma and 2 sigma occupied, 3 sigma is occupied, 4 sigma is not occupied. Overall, the bond order is 1. It's 1. Alright, it's 1. This 2 cancel. Now finally, I want to tell you this. How do we simplify the MO diagram? How do we analyze a MO diagram as complicated as this? Again, this 2s may form a sigma bond with this. The 2s may form a sigma bond with 2pz. Same here. This 2s may form a sigma bond with 2pz of carbon or 2s of carbon. Okay, let's make it easier. Let's allow just this 2s and this 2s interact. Okay, and then you have 1 sigma g 2 sigma U. That's it. Okay, 1 sigma G, 2 sigma U from the 2s of carbon and 2s of oxygen. Alright, and then 2pz of carbon and 2pz of oxygen can have head-to-head interaction. Right? They form a sigma bonding orbital here and a sigma star. Alright, that's it. And then let's talk about the interaction between the MOs. So this is 1 sigma G. Okay, it's sigma G. This is also sigma G. So these two interact. Alright, that will bump this down, bump this up. Now this 2 sigma and 4 sigma both are antibonding sigma orbitals. Alright? So that will also, shift this 2 sigma down and shift this 4 sigma up. Okay, that's why this 2 sigma has even lower energy than this 2s. Okay, before the mixing, the 2 sigma is supposed to be here. And this 2 sigma interacts with 4 sigma. Again, that will bump the lower MO even lower, the higher MO even higher. That's why this 2 sigma has lower energy than the 2s orbital, shown in this MO diagram. Now let's look at the shape. So look at this 1 sigma. Roughly it's just 1s and 2s. 2 sigma roughly is just, again, it's just the interaction between s orbital. But due to the severe mixing, again, I'm telling you, this 2 sigma and this 4 sigma have the same symmetry, so they interact. So there's going to be some P involved, and the P actually significantly lower the energy of 2 sigma. Now pi orbitals, they're very simple. 2px, 2px, 2py, 2py. 3 sigma, okay, again this 3 sigma initially is the 2pz interacting with this 2pz. But then this 3 sigma is a little contaminated by this 1 sigma, so it's not shown here. So there's a little bit S character in here. And again, this is pi star antibonding. This is simple. 2px, 2px, 2py, 2py. Finally, for sigma, we have 1, 2, 3 nodes with the highest energy. All right, 1, 2, 2 nodes. 1 node here, 0 node here, 0 node, 1 node, 2 nodes, 3 nodes. So in general, if you see the shapes of MOs, qualitatively you can rank the energy of MOs by looking at their the number of nodes. If they have the same symmetry, so you can compare sigma orbitals, you can compare pi orbitals separately. This is more complicated. You have iodine, you have chlorine. So the valence electrons of iodine interact with the valence electrons of chlorine. What about the core electrons? Let's say 4s, 4p from iodine. They are way down there, so it's just much lower than this one. So they don't participate in chemical reactions. In chemistry, we care about valence electrons. We don't care about any core electrons. And now again, 2s interact with 3s of chlorine, and this 5s of iodine can also interact with 3pz. This 3s interact with this 5s and also interact with 5pz over here. And similarly, they have pxpy, pxpy forming pi and pi star. Alright, and similarly they have 1 sigma, 2 sigma, 3 sigma, and 4 sigma. And similarly they have 6 sigma electrons. 4 are bonding electrons, this 2 and this 2. 2 are anti-bonding electrons. These 2 are actually anti. I want to call this anti-bonding electrons because again, you imagine this 5s and this 3s form this sigma G and this sigma U star. And then you put 2 electrons here and 2 electrons here, alright? And then the bond order is 0. And now 2pz and 2pz, they form a sigma bonding and another sigma star, alright? And then you have 2 electrons here, therefore the bond order is 1. And then if you're talking about sp mixing, alright, so this 1 sigma interact with this 3 sigma, they will bump this down, bump this up. Similarly, 2 sigma and 4 sigma will interact. That will bump 2 sigma down. That will bump 4 sigma up. So that's the SP mixing explained without looking at this many red lines.